TRIM is the Tropical Rainfall Measuring Mission. It was launched in November of 1997, originally designed as a 5-year mission, but we've gone now for 15 years.
15 years and thousands of storms later, TRIM has contributed to the advancement of scientific milestones. TRIM has advanced research in the areas of agriculture, disease tracking, precipitation physics, and natural hazards.
We get roughly 3 hourly rainfall estimates across much of the globe at fairly high resolution. And these rainfall estimates are used to monitor major rainfall events and to look for events that might lead to significant flooding, even landslides. And there are a number of groups that have been using it as sort of an early warning system.
TRIM's unforeseen longevity has provided more robust information on weather and climate patterns that can only be seen after years of observations. This decade and a half of data lets scientists see variations in rainfall from year to year, how El Niño affects rain patterns worldwide, and the anatomy and life cycle of major storms, like hurricanes.
It's also proven to be an extremely useful satellite for understanding hurricanes, partly because its orbit stays within the tropics, so you get much more frequent observations. And it's just provided a wealth of rainfall information over its relatively short time period that in many ways surpasses all of the information we had prior to that.
From giant storms to individual droplets, TRIM also provides scientists with data on the precise physics of falling raindrops.
TRIM has a unique set of instruments, including the first and only precipitation radar in space. It also has a microwave imager, which is an instrument that can give you the equivalent of like an X-ray of a storm, whereas the radar is giving you more of a CAT scan of the storm. It provides extremely valuable information on the rainfall structure of storms, which tells us something about how the storm is responding to its environment, whether or not it might intensify or weaken in the upcoming hours.
Building on TRIM's success will be the Global Precipitation Measurement, or GPM, mission. Its two instruments are more advanced and more sensitive versions of TRIM's microwave imager and precipitation radar. GPM's orbit will also extend coverage beyond the tropics and provide measurements of light to heavy rain and snow, expanding TRIM's legacy into the future.
Operation Icebridge has now returned to the Pine Island Glacier not once but twice in 2012. And the year-old giant crack in the glacier, poised to create an iceberg the size of New York City, well, it's still there, and that iceberg has yet to break free. But the rift has grown longer, much wider, and spawned a secondary crack. Before we talk about when that mighty berg will be born, let's take a look at the Icebridge missions themselves. Icebridge's first return to the glacier was a high-altitude flight over the entire region, including the Thwaites, Smith, and Kohler glaciers. After this campaign is over, scientists will be able to compare this broad survey with previous year's measurements in order to better document the rapid and widespread changes in the region over time. For the second mission, NASA's DC-8 flew, as it does for most Icebridge flights, at 500 meters above the ice. And this mission was about creating a brand new set of data. The flight lines took the team over previously unmeasured tributaries of the glacier and also surveyed the bedrock below them to provide a baseline for measuring change in the future. So while this focus on the Pine Island region, NASA Goddard calving specialist Kelly Brunt says the ice in the region is substantially thinning and its flow is accelerating.
Ultimately, the change that we see in that whole region, not just Pine Island, but also its neighbor Thwaites Glacier, this change represents the largest input to sea level rise from an Antarctic source.
The rift has been an intriguing phenomenon to watch over this last year, but is it a really important event?
When we talk about Antarctica and we talk about the health and state of our ice sheets, we talk about mass balance. And what you have on one side of the mass balance equation is accumulation or snowfall coming in. And when we talk about balance, that has to be balanced by things coming out. And in Antarctica, that happens either through surface melt or basal melt, or the big number in Antarctica, which is calving. Calving accounts for 80% of that side of the equation. So when you see calving in Antarctica, even calving where we use small states or the island of Manhattan as a unit of measure, this is generally very normal. It's part of the process.
However, Brunt says once the glacier calves, the new calving front will be further upstream from any calving front we've seen in the last 40 years.
I've used the analogy of a fingernail to talk about calving. Generally, if your nail breaks in the white, it's normal and you don't worry about it. If your nail breaks below the white, you think about it, you remember it. If you lose your whole nail, that's a big deal. Much of the calving, the 80% of the net loss through calving, can be equated to losing the white part of your fingernail. Things that we saw in the early 2000s in the Antarctic Peninsula side, the Larsen A, the Larsen B, that's equivalent to losing your whole nail. What's going on in Pine Island is probably that intermediate, that we've broken our nail and it's below the white, and it's something to watch and something to monitor over time.
As a byproduct of the recent ice bridge flights, the team got some great views and measurements of the evolving crack, which has been filled in somewhat by blowing snow. The crack appears to have only a short distance to go before a new iceberg is born. It's still hard to know when that will happen, but conditions seem to be right.
Sea ice acts as a buttress or a dampener for sea swell that actually protects the front of these ice shelves or the front of these floating glaciers from calving. So the fact that there's no sea ice in front of Pine Island Glacier right now implies that it might be in a state that's sort of primed to calve.
After Icebridge heads back home from this campaign, its data will be used to monitor the state of Antarctic ice sheets, while satellites will continue to watch the rift in the Pine Island Glacier as the melt season continues.
The goals of the mission are to determine where the charged particles in the Earth's radiation belts come from, how they get energized, and how they're lost into space. Each of the two spacecraft carries 5 instrument suites and a total of 8 instruments. The two spacecraft are identical. One of the instrument suites on the spacecraft is the ECT suite, and this instrument suite consists of a set of instruments. The HOPE instrument measures the coldest plasma in the Earth's radiation environment. MagIce measures intermediate energy ions and electrons. Next instrument up is REPT, and it measures still higher particles. The RB SPICE instrument measures ring current particles and their composition. The ring current is a region of charged particles around the Earth that greatly affects the Earth's magnetic field. The RPS instrument measures the radioactive particles in the inner radiation belt. The EFW instrument measures the electric field, and it spectacularly consists of very long wires that extend 40 to 50 meters out from the spacecraft with little balls on the end that measure the sensitive electric field in space. The EMPhASIS instrument suite comprises 2 instruments, a magnetometer out on a boom that measures the ambient magnetic field out in space, and a search coil magnetometer that measures wave activity in the magnetic field. I'm excited about this mission because it's going to provide answers to questions that we've been asking a long time about where the particles come from in the Earth's radiation belts, what charges them up, and what causes them to move around. I've been wondering about this a long time, and I'm ready to learn the answer.
If you wanted to learn more about the history of the Earth and other rocky planets in the solar system, where would you look? For years, scientists have turned to one of the solar system's most common features, impact craters. Left over from earlier periods of our planet's history, these sometimes giant holes in the surface can teach us about the Earth based on how they've changed over time. However, since even the newest impact craters in the Earth have changed due to wind, rain, snow, and even lakes filling them, we need to compare them to a fresh crater that still looks like it did when it was first created. So where exactly can scientists find a crater like this? Certainly not on Earth, but there's one on the Moon that's just about perfect. The Linné crater, a small impact crater located in the western Mare Serenitatis, is extremely young, and scientists have always thought that it might be a great example to use to compare with other craters. Now, thanks to high-resolution three-dimensional data generated from NASA's Lunar Reconnaissance Orbiter, scientists are sure of it. So why use a crater on the Moon, and why this specific example? Unlike craters on Earth, and even Mars, many moon craters are well preserved because they erode much more slowly. However, despite that, not all moon craters are ideal for comparison. After a crater is first formed, it can be impacted again and again by other objects, which modify its original shape. This is why scientists have been looking for a crater that's not so beaten up, and one that preserves all the telltale signs of how impact cratering works. The Linné crater fits the bill perfectly. By looking at the data from LRO's LROC instrument, scientists have confirmed that it has remained largely untouched aside from normal wear and tear, which is what makes it so perfect for comparison. They've also discovered some interesting and unexpected things. For decades, lunar scientists counted on the simplest craters, like Linné, as being bowl-shaped. However, thanks to the new data, scientists have discovered that they actually resemble an upside-down cone. This, along with other findings, sheds new light not only on Linné crater, but also on the evolution of similar craters on the Earth, Moon, and other planets, allowing us to get a better picture of our own history. In fact, the simple shape of Linné, and the way large boulders are strewn around its rim, are the basic tools of forensic geology that allow scientists to understand how craters start out on the Earth and Mars before water and wind wear them away. Without craters like Linné on the Moon, we wouldn't know how landforms evolve over time in the presence of weather, climate change, and other factors. And all by looking at what initially appears to be just another hole in the ground.
My name is Bridget Hessman, and I'm a planetary scientist at NASA's Goddard Space Flight Center, and I study storms on Saturn. A great white spot is a massive storm system that erupts on Saturn about once every Saturn year. The great white spot that erupted in December 2010 first presented itself as this fluffy white storm cloud that popped up in the northern hemisphere. The storm, when it erupted, sent large waves up into the stratosphere, and we saw effects like an increased amount of ethylene, something we never expected to see. In the coming days, the winds on Saturn sheared the storm in both directions, and it wrapped all the way across the planet. If you were to scale that to a storm system here on the Earth, what you would have is a storm system that covers all of North America but wraps around the entire planet. There'd be no escaping this storm system, and it would be lasting for a very long time. This great white spot happened to occur 10 years before we expected it, which was very fortunate because we happen to have a spacecraft called Cassini in orbit around Saturn. And that spacecraft has a full suite of instrumentation that allows us to study this over all wavelength ranges. Some of the effects that we got to see in the infrared were these two bright beacons that started to shine right after the storm erupted in December. Those beacons at first showed temperature differences of about 20 Kelvin, which is reasonable for a storm. However, as time progressed, we started to see even larger temperature changes. By May 2011, the two beacons had merged into one, and we saw a temperature change of over 80 Kelvin from the quiet conditions before the storm. So that would be like going from the depths of winter in Fairbanks, Alaska, to the height of summer in the Mojave Desert, all in one storm system. Can you imagine what that would feel like sitting on your deck? We'd never before been able to study a storm system of this magnitude in the infrared, so we are very fortunate at this time to have a spacecraft in orbit allowing us to make a historical record of this great white spot.